Hi. In the previous segment, we introduced relations as subsets of Cartesian products. In this one, we shall look at some operations one can perform on these relations. First, we look at two operations on a single relation, namely the building of its converse, also called its inverse, and building its complement. The converse of a relation is produced by taking every pair in it and flipping it. That is, exchanging its first and second component. We write the converse of a relation R by giving it simply the exponent minus 1. Note that if the original relation went from A to B, then its converse must go from B to A because we flipped all the pairs in it. Also, it means that the converse of the converse is the original relation again. Remember that a relation from A to B is just a subset of the cross product A cross B. That is, it may contain some pairs from A cross B, but may not contain others. The complement of a relation from A to B is just the set of pairs in A cross B that are not an element of R. In other words, it is the product A cross B minus the relation R. The complement is denoted by a bar over the relation. Unlike the converse, the complement has the same direction as the original relation. If R is a relation from A to B, then so it is its complement. However, similar to the converse, the complement of the complement is the original relation again. A word of warning regarding notation. There is no firm standard for denoting converse or complement. When using symbols, the complement is often indicated by striking through the symbol, while the converse is often denoted by reversing it. Converse and complement are occasionally confused, in particular when the source and the target are the same set. So let's look at the differences in the digraph representation. Suppose we have this relation R over A. Its converse, R to the minus 1, looks like this, while its complement, R bar, looks like this. Looked at as digraphs, you can think of the converse as inverting all the arrows, which also incidentally means that the number of arrows remains the same, which means that the number of tuples in the set that represents the relation remains the same. While the complement can be obtained by drawing exactly those arrows that the original diagram did not contain. Now suppose we have finite sets A and B and a relation R from A to B. What can you say about the cardinalities of R's converse and of its complement? The cardinality of the converse is the same as that of the original relation. And the cardinality of its complement is the cardinality of the entire Cartesian product of source and destination minus that of the original relation. We can also look at converse and complement in the table representation of a relation. Suppose this table represents the original relation over A. then one can obtain its converse by mirroring it at its diagonal. Its complement, on the other hand, is produced by flipping zeros to ones and vice versa. Converse and complement were operations on a single relation. Next, we shall look at an operation on two relations called composition. Suppose you have three sets, A, B, and C, and two relations. One relation R from A to B, and another relation S from B to C. The key here is that the target of the first relation, B in this case, must be the source of the second. Then one can compose the two relations and get a new relation from A to C as follows. Two elements, A and C, are related in that composition if and only if there is at least some element B in the middle set B, such that the first relation R connects A to B and the second S connects B to C. The resulting composition is written S composed with R. That is how you can read the circle between S and R. For historical reasons, the second relation is somewhat confusingly written first. Viewed as digraphs, given these sets and relations between them, this would be the relation from A to C resulting from composing R and S. You can think of it having an arrow whenever there was a path from A to C via the intermediate set B through the relations R and S. In general, a relation from A to B can relate any element of A to any number of elements in B, 0, 1, or more. The image of an element in A under a relation R is just that set of elements of B that R relates to it. If instead of a single element in A we have a set of them, the image of that entire set is simply the union of the images of the individual elements. For example, remember the bow tie relation among European countries, signifying the existence of a land border between them. What is the image of F under that bow tie relation? And what does it mean in this context? The image of France under the bow tie relation is Spain, Belgium, Germany, Switzerland, and Italy. Those are the countries in our original set C that have land borders with France.